Hello, it's Keith here, and this is lesson 26 of my Z80 programming tutorials. Now, we looked last week at the MSX, and that was quite a complex system with regards to its bank switching, so we're going to do something a bit more simple this week. We're going to look at the ZX Spectrum. Now, like the MSX and the Amstrad CPC, the ZX Spectrum is capable of 128 kilobytes of memory, and this means we have to do some bank switching. However, unlike the other systems, the basic system is not 64K, it's only 48K. And this means that the memory mapping is actually based on there being a 16 kilobyte bank of ROM in memory at all times. Also, unlike the other systems, there are actually two quite distinct versions of the ZX Spectrum when it comes to bank switching, and they work very differently. So we're going to look at that as well. So let's start by looking at the theory of the hardware and how the bank switching actually works. Now, the first thing to understand is there are two basic versions of the ZX Spectrum. There are the original versions, and then there were the versions after Amstrad took over and changed the hardware. And the reason this is very important is because Amstrad added an extra bank switching option to the later versions, and this was because they wanted to port CPM to the ZX Spectrum. As I said before, most ZX Spectrums have a ROM bank at 0000 to 3FFF. And this means it's impossible for the CPM disk system to work on those machines because the CPM disk system needs to be able to change the interrupt handler and the OSTs, and they're in the first 64 bytes of the memory address range, so they needed to be able to get RAM into that range. So the later ZX Spectrums were upgraded with an added memory function that allowed RAM to be in all of the banks, which would be very good for us as a programmer. However, unfortunately, the vast minority, only about 15% of ZX Spectrums have this function, so in practice we can't really use it. However, we're going to look at it today and we're going to learn how to detect it if you do want to use it. So in memory banking terms, there are two different versions of the ZX Spectrum, and quite unusually, the Plus 3, which is of course the Amstrad disk version, all has this extra banking mode, and some of the Plus 2s have it as well. The reason for this is when Amstrad took over and released the first Plus 2, they used the original hardware, so the early Plus 2s, which are noticeably grey in colour, are basically a Spectrum 128K with a tape drive attached to them. But the latter Plus 2s, which are black in colour, although they still have the built-in tape system, are actually the memory banking hardware of the Plus 3 system. But as I say, they make up the vast minority of the market. Okay, so what about our more common 128K Spectrums that don't have the extra Plus 3 functionality? Well, as I said, the first bank is always ROM. The second bank is the bank 5, which is the screen memory for the main screen buffer. Then we have bank 2 of RAM, which is our main RAM for our game and things, and then we have another bank at C000 which can be screen 2 and it can do other things as well, and on the Plus 3s it's used for the disk system. Now when we swap memory on the regular ZX Spectrums, it's that C000 to FFFF range that is banked in with the alternate banks, and of course because we've only got 3 banks visible normally, we have 5 alternate banks we can page in, but we can only page them into that position. Rather unfortunately, that is the screen position for the second screen buffer, and this caused a lot of trouble when I was writing the Chibi Akumas on the ZX Spectrum, because this wasn't a problem that any of the other systems had. I could always page switch in one of the other memory banks, but on the ZX Spectrum it just wasn't possible. So it meant I had to sort of cache memory for sprites and things if I was trying to write them to the second screen buffer. But that's an unfortunate thing we just have to deal with. So that's the first problem, but there unfortunately are a few other problems. So I've already said that the only pageable memory buffer is the one that's used by screen 2. That's the first problem. The second problem is the 48K systems can't actually do hardware page flipping at all. So your only option for flipping between two screen buffers is actually to copy the second one using a command like LDIR or similar to the first one. So you would effectively copy 8 kilobytes of memory from the C000 range here to the 4000 range here. On the 128K systems, you can hardware page flip, so the screen will just point to this area and you have to copy nothing. On the 48K systems, there is no other option. You've got to software copy the data. So that's another reason why Chibi Akumas doesn't support the 48K systems. First was lack of memory. Secondly, hardware page flipping can't be done. So that's our second problem with the ZX Spectrums. Now, the third problem is actually relating to the Plus 3s again. I said that they've got this much nicer memory banking option that we unfortunately can't use because it's so rarely supported. But even worse than that, even if we don't use that, ZX Spectrum, like most 8-bit systems, has something called contention. Now, the video memory is being accessed all of the time to update the screen, and this means that the memory banks used with the video memory are quite a bit slower. However, because of the memory layout on the ZX Spectrum, it's not just the memory banks that make up the screen, so bank 5 and 7, that are slowed down. 2 of the other banks are also slowed down. on the original ZX Spectrums, i.e. up to the grey +2, it's bank 1 and 3 that are slow, and banks 2, 0, 4 and 6 are fast. However, on the black +2 and the +3, the Amstrad models, blank 2 is fast, bank 0 is fast, but it's blanks 1 and 3 that are fast. So the slow banks are different on the 128K Spectrum and on the +2 and +3 by Amstrad. Now, if you were going to be very clever, you could detect the hardware, and I'll show you how to do that, and then you could alternate the banks you use for different tasks, using the slower banks for less important things like sprite data, and the faster banks for important things like game code. But what I did in Chibi is I basically treated RAM Bank 2 and RAM Bank 0 as the fast ones, and I just treated all the other ones as the slow ones, so that I didn't have to do any self-modifying code and extra testing for the complexity that it would have taken. But it's really up to you. I just wanted to make you aware that there is this contention problem where the screen banks are slower, but also these 4 banks could be slower depending on which version of the Spectrum you have. So yeah, more trouble with the 128K systems. So I'm probably sounding a little bit negative there, and I apologise for that. But the ZX Spectrum's memory banking isn't that bad, and especially if you don't need 2 screen buffers. And a lot of games can get away with not using 2 screen buffers. It's just a heavy scrolling game like Chibi. It's not really possible to avoid it. So how does bank switching work on the ZX Spectrum? Well, like most Z80 systems, we use ports, and we use an out command to write to 2 ports to select the memory banking and also the ROM banking. So with regards to basic 128K banking, that's the original Spectrums, not the +3 model, we use 3 bits, bits 0 to 2, of port 7 FFD. Now, apart from that, these other bits do other things, and this comes into something that's quite important on the Spectrum. We can't read from these ports, so what we do is we store a backup of the data that's in those ports. So if we want to change the memory bank, all we would do is we would read the backup, which the system stores at 5B5C, so we would read that in, clear these 3 bits, set the new bits we wanted, and then write it back to support 7 FFD, and of course it is a 16-bit port on the ZX Spectrum, so we have to use B and C to set the port number. Now, very simply, whatever number we put in here is the bank that will appear in this slot, and we can use 0 to 8, and it's possible to have the same bank in 2 positions at the same time. So we could have RAM Bank 2 here and RAM Bank 2 here if we wanted. I don't know why you would want to, but you certainly can. So that's a good option on the ZX Spectrum. We do have that option. Now, with regards to ROM banks are always in this 0 position here, and they are controlled by 2 bits, this bit here and this bit here, which are combined to give a ROM bank number from 0 to 3. Again, with port 1 FFD, which does the second bit of the ROM banking, we do have a backup, which is 5B67, and so we would again read in from that, wipe the ROM bit, set it again if required, and then that will allow us to update but keep the other settings the same, because you can see here the printer strobe and the disk motor are also using the same port, and here you've got the screen page bit, which again only works on 128K systems, but if we set this to 1, we would be using this screen buffer here for our visible screen, and of course this is hardware, so it's absolutely instant. We could flick between 2 screens very quickly if we want on the 128K systems. We couldn't do that on the 48K systems because we would have to copy 8 kilobytes of memory to the 4000 range where the screen is always at on the 48K systems. So 128K banking is very simple. What about the +3 banking? There's banking on the ZX Spectrum +3 and the black +2s. Well, unfortunately, it's not as flexible as the very simple banking of the 128K systems. We set this page bit here, which is by default 0. We set this to 1. Then this bit here and this bit here will take on a new purpose. They are substituted for a banking option, which is a +3 specific option. We have 4 possible banking modes. We have this option here where all 4 banks of 16K memory are using consecutive RAM banks from 0 to 3. We have this option here where 5 and 7 are in the same place and the lowest bank is 4 and the middle one is 6. Then we have this alternate one where the top bank is 3, and then we have this flipped one where the second screen buffer is in the 4000 range. And if you remember, these are actually kind of similar to the options that the Amstrad CPC 6128 had, which is swapping the screen buffer over and paging in an alternate bank at the top. So I guess you can see the kind of Amstrad influence in here, but they only gave us 4 banking options, which is very limited really compared to the Amstrad CPC's more flexible ones. So what are we going to do today? Well, just like we did on the Amstrad CPC, we're going to create two commands. One to page in a 128K bank using this option here. And this is going to be the one that was actually taken from the Chibi Akima's code. So I can assure you it works because it worked for Chibi Akima's. And then we're also going to look at how to detect a Spectrum Plus 3 by turning on its bank switching, which will have no effect on a 128K system. And just like in the past, we're going to test for the presence of 128K banks by writing some bits, turning off the banking and checking if the bits were written or not. Because if the banking isn't available, turning it on will do nothing. So we will have written the data to our normal bank. Okay, so let's have a look at the actual source code we're going to use today. So as before, we're using this bank swap test, which is a very simple command. All it's going to do is it's going to use the get hardware version, which returns 2 bytes defining the current system. We'll show them on screen, and then we're going to play with the banking a bit on the Spectrum. So we're going to set bank 1. We're going to store the byte relating to bank 1's number at the base of the bank, which is going to be C000. We're then going to switch in bank 2 and do the same. Then we're going to switch in bank 0, show the contents of bank 0, show the contents of bank 1, and then the contents of bank 2. So we will confirm the bank switching is working, and we will be able to see that. And we're also going to see what system we detected. Well, how are we going to detect the system? Well, here's what we're going to do. As before with the Amstrad, we're going to use 2 registers. The D register is going to be used to detect the hardware version. So if we have a 0, we're going to have a 48K or a regular 128K system or a grey +2, not with the +3 banking option. If we have a 1, then we have the +3 banking option. So we've got a black +2 or the +3. Now the RAM, we're going to detect either 48K or 128K. So obviously this gives us the ability to detect a Spectrum 48K, a +3 or a 128K that isn't a +3. Now if you want to cheat a little bit and use some simple code, one way to detect these systems is to read the ROM and to compare a known byte and see which one it matches with the known ROMs of these systems. However, there's a lot of clone Pentiums out there in Russia and things, and they can use alternate ROMs, and of course the Western machines can also have had custom ROMs installed, so that's discouraged, and it's not something I did with Chibi Akima's, and it's not something I'd recommend you do unless you really want to, and you'll probably get criticised for it. But you know, it depends what your compatibility targets are and how much effort you want to put in. If you just quickly want to detect a +3 or a 128K or 48K, it's up to you. But anyway, we're not going to do that today. We're going to page in the banks and see if the paging options work to decide what system we've got. So what we're going to do here is you run this bank test command on bank 7 and see if it works. And the bank test command is identical to the previous week's version. So we're going to write the byte 69 to bank 0, which is our default bank. We're then going to page in our alternate bank. We're going to flip the bits, page back in bank 0 and see if our 69 is there. If our 69 is still there, then this bank switch worked. If the bank 69 is no longer there, then the bank switch didn't work and this has corrupted that byte. So this allows us to see if the basic 128K bank switching works. We're going to do the same for the +3. We're using a slightly different command because it's a little bit more tricky. As I said before, we have to set this special paging bit here, and then these 2 bits define the bank we're going to switch in. So let's have a look at what option we've decided to use. Well, we've used this option 0 here. These numbers should be different. I'll have to change these. These should be 0, 1, 2 and 3. So we're using this option here. The reason for that is RAM bank 2 is at the 8000 range. Now that is the same as our normal system, and the reason that's important is because that's where our code is. If we paged in any of these other options, our code would crash. It is also important to notice that the stack is at the 4000 range, so we're not going to be able to use the stack while we're paging. We also won't be able to write anything to the screen, but that's not going to matter. Also, another problem is these are also in that 4000 range, so we're going to have to back them up first, and that's what we're doing here. We're backing them up into some spare registers. We're paging in bank mode 0. We're then paging in the bank here. We're then paging in bank 0 here because I was having some trouble where this was actually changing the 128K banking options on the non-+3s. So for safety, we're setting a proper bank there. I don't know quite why that was. It didn't seem it should do it from the documentation, but it certainly was happening. Now we're going to flip the bits at the C000 range, and then we're going to turn the banking off, and we're going to see if the bits have been written or not. If we get to here, then we have got a +3 system, so we're going to increment D. So that's how we get D to be the Spectrum version and E to get the memory. So now what we need to do is have a look at this set current command. Well, the set current command is pretty straightforward. It's taken straight out of Chibi Yakima's, and what it does is it will read in the backup of the 7FFD register, which is the one we need to change to set the memory, remember? It's this one here. Now the backup symbol is pointing to this here, so we're just using that. And then what we're doing is we're clearing out the 3 bits that define the memory. We're then ORing in the new definition, which is going to be in C at this point. We're loading it in from A here because we need to use A at this point. And then we're just outing it to that port here, and we're storing the new version here. Now, the idea of set current, reset and set is this. In Chibi Yakima's, there were times when we needed a default bank for general purposes, so the level would start, the level code was in, let's say bank 5, I can't remember. So then you would set the current bank to bank 5. Oh, but the music needs to play for a moment, and the music's in bank 2. Well, you would then use the set command here to switch to bank 2 with interrupts off. You would play your music, and then you would use the reset command, which would switch you back to whatever bank was set with the last set current command. So you can see that the set current, set and reset are a way of having a permanent bank using set current and a temporary bank with set and reset, and it worked pretty nicely. With hindsight, maybe I should have used pushes and pops because that would have allowed nesting, but I was learning when I wrote this, and it did a really good job, and to be honest, it did just fine. So I've put it into these tutorials here. So we also have some other options with regards to the firmware here. One thing I will tell you as a word of caution, which I learned the hard way, there is a special part of Bank 7 that is used by the Spectrum +3 disk system. The area DB00 to E7FF is used by the disk system, and while other parts of it of Bank 7 are also used by this disk system, in most cases you can wipe them and the disk system doesn't care, but the disk system needs this bank back if you're going to use the disk system again. With Chibi Yakima's, I was actually backing up this area to a piece of spare space and then restoring it later because Bank 7 was being used by the screen and also the second sprite buffer. So I really needed that space, but the disk system needed it to be intact when it came to reusing the disk system. So that's something I learned, and so I've put it in here in the hope that some of you can learn from my troubles, because it really caused some problems for me. It actually caused the game to crash on the last level because the last level had the bigger sprites with that big pre-rendered background. So yeah, that was a bit of a trouble for me. Now these are some options that were just taken from the Chibi Yakima's code with regards to turning the firmware ROMs on and off, but we're not really going to look at those today. And you've just got a very quick sort of cheat sheet here for the RAM and ROM bank switching. So there we go. So it's a pretty easy example, and as I say, if you're not interested in how it works, all you need to do is use this set current command with a bank number in A, and that will switch in a memory bank into the C000 to FFFF range, and then you can use all of that extra 128K memory. So let's have a go with our example today. So we're going to run it first on a 128K Spectrum. That's not a +3. So you can see here D is 0, and if you look, that is what we expected, because 1 would be a +3, and this is not a +3. But we do have a 1 here, and that means we have a 128K bank. And we can see this here because we've bank switched in 3 times, and you can see bank 0 contains the 96, which is remaining from our testing of the bank, 01 in bank 1, and 02 in bank 2, and it looks like we've probably overwritten something there, but never mind. So you can see our bank switching is working. You can see we've detected it's not a +3, and we've detected the 128K of memory. Let's see that again on the +3. Well, you can see again we've detected 128K of memory, but this time we have detected the +3. And again, we have the exact same 3 memory banks with basically the same data in them. So the 128K banking does work on the +3 and the 128 just fine. It's the +3 banking that only works on the +3, and that's how we've detected the +3 today. So finally, let's see it again on a basic 48K Spectrum. So here it is. We've got a 0 here because we're not on a +3 system. We've got a 0 here because we're not on a 128K system. And you can see here now all of these banks just contain 02. And that's because the bank switching didn't work in our test. So the last data that we wrote to this base area here was bank 2's number, which is 2. And that has been written and is being shown to the screen in what is effectively the only bank. These bank switching commands have no effect on a 48K system. So there we go. So you can see it's very easy to switch between the banks, and while the bank switching is a little bit frustrating because of the forced ROM bank at the 0 range here, and because of the inconsistent contention between the 128K and the Plus 3, to be honest, it's not too worth worrying about. I was worried the contention would really slow down Chibi Akums, but it doesn't at all. Chibi Akums is pretty fast on the Spectrum, and it's actually still faster than the Amstrad anyway, because the screen on the Spectrum is 8K, whereas on the Amstrad it's 16, and that's far worse than any contention for slowing down the game. So don't worry about that too much, and if you want to use the 128K systems, you've got loads of extra memory to play with, so hopefully you can do something good with them. Okay, I hope you've enjoyed this week's lesson. Next week we're going to be doing a rather strange system, the Elan Enterprise, which a lot of you may not have heard of, but it's a really great system and it offers some of the most powerful memory banking you could ask for. So please tune in for that and we'll have a look at the Enterprise. Thanks for watching today and goodbye.